In the last lecture, I presented furnace efficiency, fuel saving, carbon offset concepts and exercises. The concepts behind furnace efficiency, fuel saving were presented in that lecture, and I tried to clear the concept by solving some problems over there. In this lecture, I thought of to solve few more problems so that you understand the concept of furnace efficiency, fuel saving and carbon offset, because particularly when we talk of energy saving in industrial furnaces, so it is the furnace efficiency is very important, and the factors contributing to the furnace efficiency were already discussed. Now, let me solve few more problems to clear the concepts. So, I will be presenting to you first of all the problems which I am going to take. The first problem: a given metallurgical process and furnace has a gross available heat requirement of 1.5 into 10 to the power 6 watt and a critical temperature of 1371 degree Celsius. The furnace is fired with dry pulverized coal containing 70% carbon and having a low calorific value of 27,900 kilojoule per kg. Now, here I will like to tell you that please read the problem very carefully, because for the calculation, how carefully you read, that will help you. For example, one is that I am telling the critical temperature of 1371 degree Celsius. That means that the flue gases will also be living at the temperature of 1371 degree Celsius, point number 1. Point number 2, it is said in this particular problem that coal has a low calorific value of 27,900 kilojoule per kg. That means that here the calorific value of the fuel is given by considering the gaseous state of the products of combustion, for example, C to CO and H to H2O vapor. So, that is important, because while calculating the heat taken by the products of combustion, the standard state for input and output must be same, otherwise there will be an error in the solution of the problem. The dry combustion air is preheated with the heat recovered from the flue gases in a heat exchanger having a relative efficiency of 50%. Now, the concept of relative efficiency, furnace efficiency, regenerator efficiency were already introduced in the earlier lectures. So, please get the concept from there. The flue gases have the following analysis: percentage volume on wet basis, 7% oxygen, 12% CO2, 5% H2O and 76% nitrogen. You have to calculate first, calculate the coal consumption in kilogram per hour when the air is not preheated and the flue gases leave the furnace at the critical temperature. So, that critical temperature also the exit temperature of the flue gas, that is for the assumption that you are making in this particular problem. B, calculate the coal consumption in kilogram per hour when the air is preheated, the flue gases leave the furnace at the critical temperature. C, assume the heat exchanger is not used, but instead the coal is burned with a mixture of cold air, that is 25 degree Celsius and oxygen. Also, the excess of oxygen in air and pure oxygen combined over theoretical for combustion will be kept same. Now, this is also important to know while solving the problem, because excess air or excess oxygen in air and pure oxygen combined over theoretical for combustion will be kept same as with the preheater. So, calculate the quantity of oxygen required in kilogram per hour to obtain the same fuel consumption as found in B with the preheater. So, this particular problem will illustrate the role of oxygen enrichment of the air on furnace efficiency. That means, you can improve the furnace efficiency by either preheating the air or by enriching the oxygen, and the same I am going to illustrate by solving this particular problem. Problem number 2, a batch reverberatory furnace is to melt 305 tons of copper, a typical problem on melting, and heat it to 1327 degrees Celsius. Now, recall here the temperature is 1327 degrees Celsius over a period of 6 hours. The heat loss of the furnace to the surrounding over this period is estimated to be about 1/2 of that required heating and melting copper. So, the heat losses are also given, but in a different form. It is said that whatever amount of heat that you require to heat copper from 25 degrees Celsius to its 1327 degrees Celsius, half of that will be the heat loss to the surrounding. Fuel oil analyzing 85% copper, 12% hydrogen and 3% oxygen, and having a low calorific power of 9446 kilocalorie per kg is to be burned with dry air, 20% excess of theoretical requirements. The flue gases from the furnace enter a waste heat boiler, where the heat loss is estimated at 15% of the sensible heat of the entering flue gases. The stack gases leave the boiler at 316 degrees Celsius. Here estimate A, the average fuel consumption, B, air supplied to the furnace, C, heat recovered in boiler, and D, fraction of calorific value of oil recovered in the boiler. That is the problem number 2. Now, problem number 3 is a very simple problem, is a very tricky problem, and it will tell you how much of the heat balance of a furnace you have understood. Though I will be presenting the solution of all the 3 problems, but my appeal to the viewers of this video lecture is that please attempt to solve the problem before you see the solution, because ultimately you have to see that you have understood it or not. Now, this problem is very simple, but it requires a clear cut understanding of the heat balance of the various process. The problem is as follows: a heat balance for a continuous metallurgical process gives the following data. Heat input, combustion of fuel, it is 100% of the total. Heat output, process requirement takes 25% of total. Sensible heat in flue gases take 50% of total, and heat losses 25% of total. The installation of an air preheater is being considered. Now, here you consider yourself to be working in a company, and your boss has come and he has told you that, well, I want to install a preheater, I want to know how much fuel I am going to save. So, you have to tell him by installing a preheater what amount of fuel is going to be saved. So, what he is asking you? He is asking you the following 2 questions. The installation of a preheater is being considered. It is estimated that the proposed preheater would recover 1/2 of the sensible heat in the flue gases and would return this quantity of heat to the furnace in the combustion air. Now, he wants to know 2 things, because he is going to have a big investment for installing a preheater, because ultimately that preheater has to be integrated with the furnace. So, he wants to know beforehand that what fuel he is going to save in order to see whether his investment is compatible with the fuel saving or not. In fact, from the business point of view, the profit or the fuel saving should be greater than the proposed cost for installation of the preheater. So, it is with that idea he wants to know the following: A, if the daily process requirement and daily heat loss are kept same, remember, what percent saving in fuel could be achieved by the preheater installation, and what would be the new heat balance in percent? B, if the daily fuel consumption and daily heat loss are kept same, what percent increase could be made in heat furnished to the process as a result of the preheater installation? What would be the new heat balance in percent? So, that is the problem number 3. So, all these 3 problems I will be going to solve, but I will again appeal that before seeing the solution of the problem, please try to attempt yourself. So, here I will go with the solution of these problems. Problem number 1. I will try to draw a block diagram which represents the material balance and heat balance of the process. So, the process said that this is a furnace this is operating at 1371 degree Celsius. The input is you have a fuel which is 70% carbon and its net calorific value which is also called low calorific value, that is given to you 27,900 kilojoule per kg. Now, it is also the flue gases, the composition of flue gas is given. So, this is called either products of combustion or you can also call flue gas. The composition is given, it has 7% oxygen, it has 5% H2O, it has 12% CO2 and it has 76% nitrogen. So, this enters into preheater, and the preheated air which enters into the furnace this is the preheated air. This is the preheated air enters into the furnace and the exit of the preheater is again you have the same flue gas percentage, because the material is not lost, in transferring its heat, only its temperature would decrease. So, this is the output of a preheater. So, this is what the problem is given to us. Now, first of all we have to calculate the coal consumption in kilogram per hour when the air is not preheated and the flue gases leave the furnace at the critical process temperature, that is the part A. So, I will be calculating first of all A, where the fuel, where the air is not preheated. So, the case is no preheating of air, Naturally, first of all I must know the amount, because at the several places I have told that heat balance cannot be made unless you do the material balance, because you have to know what amount of material are being exiting the furnace. So, if we take for example, say let us take 1 kg dry coal. Let us take 1 kg dry coal and let us consider x kg mole is products of combustion. Then by doing carbon balance, say by performing carbon balance, we can calculate the amount of products of combustion. All that you have to see, do proper balancing, and the answer would be, if I take x kg mole POC, then x will be equal to 0.486 kg mole. Now, the next task is that to find out the amount. So, I will write down here this is the oxygen, then we have CO2, then we have nitrogen, then we have H2O vapor. Remember, that is very important. Accordingly, you should use the heat content. So, the kg moles as given to us, as we can find out by multiplying. So, kg mole, that will come here 0.034, here it is 0.05832 kg mole, then nitrogen is 0.3694 kg mole, and H2O vapor is 0.0243. Now, to find out the heat to POC, what you will require? You have to find out mCp into delta T. So, once you get the value of Cp, you have to integrate the value of Cp from 298 Kelvin to 1371 plus 273 Kelvin, and the appropriate value of CpO2, CpCO2, CpN2, CpH2O vapor you will write, integrate it and get the heat which is taken by the products of combustion. What I have done for you, I have calculated those values and I am listing you the values for heat content in the form of, say, heat content, for example, H 1644 minus H 298. This I am writing kilojoule per kg mole. So, this value for CO2 is 70,417.2 kilojoule per kg mole. For oxygen, this value is 46015.2. For nitrogen, this is 43458.8, and for H2O vapor, this value is 55,078.8. Now, remember, select the correct value of Cp of H2O vapor, not for H2O liquid. Why? Because the calorific value of fuel is given, it is the net calorific value, where the standard state of products of combustion of H to H2O is the vapor state. That is the important thing. Now, once we know the heat content value, then I can calculate from here. So, heat to POC, that will be simply in kilojoule. So, I have to multiply appropriate value. So, for I multiplied for you. So, I am getting here for oxygen 1564.51, for CO2 it is 4106.70, for nitrogen 16054, and for H2O vapor it is 1338. So, if I sum total all, then I will be getting 23064 kilojoule. Now, I know this is the heat to POC. The calculation of fuel consumption I had already introduced you. We have to calculate gross available heat available upon gross available heat per kg of the fuel. So, if you calculate that, now we have to calculate gross available heat per kg of the fuel. That will be equal to 27,900 is its net caloric value minus 23,064. So, that will be equal to 4836 kilojoule per kg coal. Now, you know fuel consumption, I am repeating the formula, though I given at several places. Fuel consumption, that will be equal to gross available heat per unit time upon gross available heat per kg of fuel. So, we know now both the values. So, if I substitute these values, that will be 1.5 into 10 to the power 3, it is given, that in kilowatt, into 3600, that becomes, now it becomes in kilojoule per hour, divide by 4836, that was kilojoule per kg. So, the fuel consumption is 1.117 ton per hour, or 1117 kilogram per hour. So, you note this is the fuel consumption without preheating. Now, let us do the second part of the problem, which says, if suppose we employ a preheater, if we employ a preheater, then how much fuel will be consumed. So, let us calculate now. So, B part said when air is preheated, when air is preheated. When air is preheated, then we have to calculate now, when the air is preheated, again you have to calculate the fuel consumption in kilogram per hour, all that you have to find out. Now, how much amount of sensible heat is being supplied to the furnace, then you can find out. So, first thing we have to find out the amount of air. So, for that I am making one assumption, say assumption which I am making, that coal does not contain nitrogen. Coal does not contain nitrogen. So, on that basis, if I do nitrogen balance, then I can calculate nitrogen from air, that is equal to nitrogen in POC. So, that way I can calculate the nitrogen from air, that is equal to, already we have calculated 3694 kg mole, and oxygen from air is 21% of this, that is equal to 0.0982 again kg mole. I have given relative efficiency is 50%. You know the definition of relative efficiency. So, relative efficiency that will be equal to, well, I again write down for you the definition, that is equal to sensible heat in preheated air, sensible heat in preheated air upon sensible heat in air at hot flue gas temperature. Heat in air at hot flue gas temperature. Now, you have to calculate all these things. So, if we do all these calculations, then we get the, then let us 50, relative efficiency given 50 upon 100, and let us say sensible heat, that is delta H1 we have to calculate, sensible heat in air we have to calculate, that is 20573, sensible heat delta H1, that will be coming 10286 kilojoule per kg of coal. So, again I have to calculate the gross available heat. You know how to calculate. So, calculate, it will come 15,122 kilojoule per kg coal. I calculate now fuel consumption. Fuel consumption, that will come out to be equal to 357 kilogram per hour. So, that means now our conclusion we can put it that preheating would save, that preheating of air would save 760 kg per hour of fuel. So, you can imagine the importance of fuel saving, the importance of preheating in fuel saving, and the consequently the effect of fuel saving is the reduction in CO2 also, that we can calculate. So, we can say now the saving in carbon, this is fuel. So, saving in carbon that will be equal to 532 kilogram per hour, because 70% is the carbon. So, saving in carbon per day, that will be equal to 532 into 20, that will be equal to 10,640 kilogram per day. Now, mind you, here I have assumed that the furnace operates only for 20 hours, not for 24 hours. That is why I multiply by 20. So, reduction in CO2, the concept already I have introduced to you, reduction in CO2, that will be equal to 39.4 metric tons. Now, see the interrelationship between carbon saving or fuel saving and the carbon offset. So, the carbon offset, the concept already I have introduced, that will be equal to 39 per day. So, this particular problem clearly illustrates the interrelationship between fuel saving, furnace efficiency, and the carbon the carbon offset and so on. Now, let us see the part C of the problem, which says that if you do not use heat exchanger, we keep the fuel consumption same as that of B, then how much amount of oxygen you have to supply. That it tells you the alternate way of saving of fuel. So, oxygen with preheater, that we already calculated, oxygen with preheater, that was 0.0982 kg mole. Now, you have to recalculate the products of combustion. Now, theoretical oxygen would be, that will be equal to 0.0705 kg mole, that we will be calculating from products of combustion which has CO2 and oxygen. Now, let us say if x kg mole oxygen is required, if x kg mole of O2 is required to have the same fuel consumption as that of preheater, what we have to do? We have to enrich the oxygen, so that the heat which is carried away by nitrogen, it decreases. That is the key of this particular problem. So, now we write down again the products of combustion composition. So, POC, say excess oxygen, that we have to keep the same as the problem illustrates, excess oxygen, that is 0.0277, mind you, they are all in kg moles. Now, nitrogen, that will be equal to 0.369 earlier. Now, I am requiring x kg mole of oxygen. So, correspondingly nitrogen will be 3.76, nitrogen will decrease. Now, CO2 that is equal to same 0.05832, H2O vapor will also be same, that will be equal to 0.0243. I will be calculating now gross available heat without preheater. So, gross available heat without preheater, that we have got around 4836 kilojoule, refer to A part of this problem, kilojoule. So, now heat balance, again you have to calculate the heat output, heat of POC and so on. So, make the heat balance. So, heat balance will be 4836, that is equal to 22754 minus 163405 x. So, if I solve for x, then oxygen required you will be getting in kg mole, we have to multiply by hour and so on. So, oxygen required will be 1252 kilogram per hour would be the oxygen required if you want to have the same fuel consumption as that of the not having preheater. So, I am going to solve now the problem number 2, and the problem number 2 already I have enunciated. Now, I will draw the block diagram, and this block diagram is as follows. This is for, it is a melting of copper. So, you are melting around 305 tons of copper and heating it to a temperature of 1327 degrees Celsius by using fuel oil. Fuel oil composition: carbon 86%, hydrogen 11% and oxygen 3%. It is combusted with 120% dry air, that means 20% excess air as is told in the problem. Now, the products of combustion, they enter into a waste heat boiler. Now, recall, waste heat boiler is also a typical device for recovery of the heat. Waste heat boiler, and it is used to produce superheated steam, and ultimately the products of combustion they discharge at 316 degrees Celsius. Now, here it is given to us heat loss is 15% of the heat input, NCV is given, NCV of the fuel is given 9446 kilocalorie per kg. This is given to us, and from the furnace the heat losses are said it is 1/2 of that required for heating. So, now we have to calculate first of all the average fuel consumption, that is the first thing we have to calculate. Now, again we have to calculate the first of all the composition of flue gas. So, composition of flue gas, we will be calculating, say you have to do the material balance and calculate it. Say CO2, I am directly calculating 0.0717, H2O 0.0275, O2 0.01615 and nitrogen is 0.4407, that is the flue gas in kg mole. Now, again I have to give you the heat content value. So, I am giving you the heat content value, say H 1600 minus H 298 for CO2, for H2O, for O2 and for N2. So, So, this value is 15,850, 13,110, this is H2O vapor, and 10,442, nitrogen is 9,943. So, that is given to us. So, we can calculate the heat to POC. So, just multiply. So, I calculated here, I am straight away writing heat to POC. You have to multiply each value by this one. So, heat to POC will be equal to 6047.5, that will be in kilocalorie. So, here the units which I am giving is kilocalorie per kg mole, kilocalorie per kg mole. So, once that is given, so we can calculate now fuel consumption. Fuel consumption, that will be equal to 9.515 plus 4.7575 into 10 to the power 6 upon 9446 minus 6048. Now, this value of 9.515, that is coming, we have to first of all calculate how much amount of it is required to bring copper from 25 degree Celsius to 1327 degree Celsius. So, for that it is given to us a H 1600 minus H 298 copper is given to you 11,980 kilocalorie per kg mole. So, from this you can calculate the heat content 305 tons, you convert into kg mole, multiply it, that will be 9.515, half of it is lost on the furnace. So, that is how you will be calculating, and this answer will be equal to 4.2 tons per hour. So, that is how you will be calculating the fuel consumption for A part. Now, the B part says, you have to calculate air supply to the furnace in meter cube per minute. Well, that is very simple. So, air consumption per hour, that can also be find out. Now, you try to find out, I am giving the answer 848, this is meter cube per minute at 1 atm and 25 degree Celsius. This is the answer for B part. Now, the C part, it says heat recovered in boiler. Now, heat recovered in boiler, that can be calculated, that will be equal to heat input to boiler, heat input to boiler minus heat output from boiler, heat output from boiler. Now, heat input to boiler is what the heat carried away by the flue gases, that already we calculated in part A. Now, heat output to the boiler, from boiler you have to calculate, because from the boiler the flue gas are exiting at 316 degree Celsius. So, if I give you the value of H 589 minus H 298, again in kilocalorie per kg mole. So, for CO2, that is equal to 2965, for H2O it is 2409, for oxygen that is equal to 2121, and for nitrogen that is equal to 2043. So, you can calculate these values, I do not need to calculate. So, if you do it, then heat recovered in boiler, that will be coming 3928 kilocalorie per kg of fuel. That is the answer for D. Then fraction of heat recovered, in reference to the calorific of the fuel, that will be simply 3928 upon calorific value, that is 9446, that will be equal to 0.42. That will be the answer for the part D. So, that is how you will be solving this problem number 2. Now, the last problem which I have said, it is a sort of a problem which tests your common sense, intelligence and your understanding of the heat balance part of this particular course. Now, again I am telling you, this particular problem which I am going to present now, that is a problem number 3, is a required little bit of your knowledge and your understanding. Let us see that. Now, this problem gives you the heat balance of a process is given to you. You think yourself that you are a manager in a plant or you are working and your boss has come and he has given you the idea, well, I want to install a preheater, give me how much saving I will be getting. So, you have to answer to him quickly. Now, the idea of this particular problem is to answer him quickly, and that is the way you will be proceeding. Please solve first yourself before seeing the solution, that is my humble request. So, the heat input, so the problem says, the problem you have to first of all find out the installation of a preheater is under consideration, and the A part is that if the daily process requirement and daily heat loss are kept same, what percent saving in fuel could be achieved by the preheater installation. So, we will make again heat balance. So, this is problem number 3. So, heat balance, let us say heat input, and on this side heat output, again in percent of total. Now, since it says it is the fuel input, so now the combustion of fuel, let us say it supplies X percent of heat is supplied by the combustion of fuel. Now, it says process requirement is say 25%, that is same. Sensible heat in POC, in the problem says 100%, 50%. So, if X is the fuel, then X by 2% will go as sensible heat in POC. Heat loss are to be kept same as per the need of the problem. So, heat loss is again 25%. So, we will just, and half of the heat is being circulated. So, X by 2 is out. So, X by 4 will be in. So, this will be sensible heat in preheated air. Okay. So, we have to do it simple, X plus X by 4, that will be equal to 50 plus X by 2. We will solve the value of X. So, X will be equal to 66.66%. So, fuel saving will be how much? Fuel saving will be 33.34%. See now how quickly you get the answer. So, now the problem says what is the revised heat balance. So, let us put it, the revised heat balance So, revised heat balance will be, say now input and here is output. Combustion of fuel, that is equal to 66.66, that is in percent. Sensible heat in air, that is 16.66. So, the total is 83.32%. Now, heat output, say process requirement, says 25%, sensible heat in POC, that is 33.33% and heat loss, that is equal to 25%, again it makes 83.33%. Now, we can refer these values to the 100%. So, if I refer to the 100%, that will come here 80%, here it will be 20%. So, that makes you 100%. Similarly, I can make it referring to the 100%, that will be here 30%, here it will be 40% and here it will be 30%. So, again you have the answer as 100%. So, you see how quickly you can answer to your boss that, well, this preheating will save you that much amount of fuel. So, he will maybe attracted to install a preheater and शायद आपको शाबाशी भी दे दे. So, now the B part says that if suppose fuel saving is not done, you consume the same amount of fuel as you have consumed earlier, then what percent increase in the heat will occur in the furnace as a result of preheater install. That means, now you are not changing the fuel consumption. So, so the part B, again we will do the heat balance. So, heat input, heat output, so heat input, the combustion of fuel, now it will remain 100%. Then the sensible heat in air, you are recovering half the heat. This 100 will remain 100, now it has become 25%, because half is coming over here. Now, heat output, the process requirement, say we do not know now, it is X, sensible heat in air, sensible heat in POC, that is 50% as it was said, heat loss 25%. So, again we do the heat balance. So, I am getting here X, that is equal to 50%. So, that means now earlier it was 25%, now it becomes 50% process available heat. So, that means I am increasing now, the percentage increase in available heat is 100%. So, now the revised heat balance would look like this. Revised heat balance, that will be, say, input, here again output, combustion of fuel, that is equal to 80% and sensible heat that is equal to 20%. Output say process is 40%, sensible heat in POC again 40% and heat loss 20%. I referred them to 100%. So, this becomes also here 100% and this is also 100%. Now, you note here how quickly this problem help you to illustrate the role of preheater in an installation. Now, with this last lecture, I have completed all the lectures in fuel furnace and refractory. Now, in all these lectures at various places I have given solved as well as unsolved problems. My appeal to all the listeners of this video lecture that please attain problem by yourself before going to the solution of the problem. Though solution is there, but it is in the best interest that if you solve the problem and develop some innovative method for the solution of the problem. Lastly, I will also like to point out that we never do after solving the problem. So, please see that you also analyze the solution of the problem. Now, it is very important that you analyze the problem, because once you solve the problem and you get the solution, you have built up yourself for the present. But if you solve the if you analyze the solution of the problem, then you are adding a value to your future career. So, again I will appeal that whenever you solve the problem, try to analyze the solution of the problem and develop a feel that what has been done. Now, this will help to develop your analytical skill, and the analytical skill is always an asset.